Hello. So good afternoon and welcome again to the second live session of my course, Power Electronics Application in Power System. So interested learners may join either using the YouTube link, or you can join in Microsoft Teams and you can directly ask me questions. So I received one question from Rahul Mitra. Rahul also joined in Microsoft Teams. So the question is, instead of two opposite-ended thyristor, can we use single MOSFET or IGBT switch in specific? See, you can use any power semiconductor switches instead of the thyristor. But this bidirectional thyristor is basically used to turn on both in positive half cycle as well as in negative half cycle. So that facility is, should be available. Okay. Now regarding the specific choice of the semiconductor device, I am not the suitable person, or I do not have much expertise to tell you. However, this any kind of power electronic switch which can withstand the required amount of voltage and current can be used. Okay. I think Rahul, I could clarify your questions. If you have any further questions, you can unmute your mic. I can see that you have joined in Microsoft Teams, and you can directly ask me the question.
Sure, thank you, sir. I understood.
Yeah, so the bidirectional feature is basically for firing both in positive half cycle as well as negative half cycle, nothing else. Okay. So in any semiconductor device you can use which can capable of, I should say, power semiconductor switch you can use which can capable of that much of voltage withstanding ability and the current carrying capability. Okay.
Understood, sir. Thank you.
Okay, so I received one question from in YouTube chat. I don't know who is that person. Is this a real university lecture or is this a question answer for YouTube? So this is live session. This is not a lecture. This is a live session where I can interact with you. Okay. So if you have any question regarding this course, this is the opportunity that you will get to interact with me. Even if you have any doubt on specific matter, you can come forward and discuss with me. So this is not a lecture. This is rather a doubt clearing session. In NPTEL, it is called live session. Okay. So it is an opportunity for me also to interact with you. And it is also an opportunity for you to clarify your doubt and concern on anything. Any question if you have, you can discuss with me regarding this course.
Sir, I have one more question.
Yes, please.
This is related to in the I think week 8 lecture you covered regarding the slope compensation part, sir. Okay.
Mm-hmm.
Where you talked about if you increase the slope by, let's say, 2%, 3%, or even 5%,
Yes.
then the power requirement to maintain it at the constant voltage, the power requirement of the SVC will be lesser, slightly lesser in comparison if you increase the slope.
Yes,
And you
yes,
showed
yes.
that mathematically also, and with you showed it with the example of equations also, sir. So
Yes.
my question here is, sir, that is there any challenge to why you kept it, or why in the numericals also it is kept limited up to 5% or so? Can we, like, if
No,
we
no,
increase the slope?
Rahul, your
Yes, sir.
question, I could not, it is not fully audible to me. Can you just repeat it with a higher voice?
Sure, sir. Can you hear me now? Is it
Or you
better?
can keep your microphone near to your mouth and speak.
Sure, sir. Is it clearer now?
Yes, yes. Speak loudly.
Sure, sir. So my question was, sir, can we increase the slope by even more? Like, instead of keeping it 5%, if we keep it like, say, 50% or even 75%, if we increase the slope, then the power requirement to maintain it at the same voltage will be even lesser. So can we increase the slope even much, much higher? Like, will there be any consequences to
No,
that?
no. This. See, you have to also, if you get any benefit or any advantage, you are losing something. So if you follow these control characteristics, you will see accepting certain amount of slope means accepting certain amount of over voltage and under voltage. Okay. So if you do not have any slope, that is 0% slope, it means that you are able to maintain the voltage constant within the control range at the reference value. However, if you have a positive slope, it means that you are accepting certain amount of over voltage and certain amount of under voltage. Now, 5% over voltage or under voltage are often allowable for any power network, 3 to 5% depending upon the of course the voltage rating. So more than that means that your SBC could not able to mitigate over voltage or under voltage fully, and you are accepting a huge amount of, for example, as you are saying that 50% slope, it means that you are accepting a huge amount of over voltage and under voltage, which are practically infeasible. Okay, so that is not possible. Some positive slope to 3% to up to 5% is allowable. It means that you are accepting certain amount of over voltage and under voltage in the control range. Okay, is it clear?
Yes, clear, sir. Thank you.
Yeah, so if you look at the control characteristics, certain amount of over this positive slope, let's say 2% positive slope, it means that you are accepting a certain amount of over voltage when your SVC is operating to mitigate the over voltage. Okay, so for example, if your system over voltage is 10%, then by using SVC maximum over voltage you can mitigate from 10 to 5%. Okay. However, there is if you consider there is no slope, it means that you are not accepting any over voltage. You are always maintaining a voltage a constant value. That is the reference value. Okay. Same thing will be applicable for under voltage as well. Is it understood?
Understood, sir. Thank you.
Okay. So any further question, those who have joined YouTube live session, can go ahead and write in the chat box, or alternatively you can join using Microsoft Teams as Rahul has joined, and you can directly interact with me. So any question related to the course, whether it is based on in the tutorial or based on the question pattern that you are expecting in the exam, or based upon the my video lectures, or anything else, if you are interested to know or clarify, then go ahead and write the question on the chat box.
Sir, one more question.
Yes, yes.
Sorry.
Yes.
Sir, you introduced the role of SVC in the power oscillation damping, like the role of SVC to reduce the damping, right? So without
Yes.
SVC, it can be marginally stable, or it can so that concept you introduced, right? And how using an SVC, we can introduce a damping constant value to make it stable. Sorry, to make it overdamped so that it eventually dies down the oscillation by allowing some small changes in the voltage value, right? So my question is, sir, that you derived the expression also for zeta, and it was coming to like a big expression. But for that to be overdamped condition, the value of zeta must always be greater than 1, right? So if it is between 0 to 1, it will be underdamped condition and it will again become unstable. So my question is, sir, is that do we have to design zeta in such a way to ensure that it is greater than 1? Or is it always a property of zeta, like that it will always be greater than 1 only, that we don't need to give any consideration for that? I just wanted to ask that, sir.
Yeah. No, your question is correct, that zeta is the damping ratio, which basically decides the damping of the system. Now, here in this particular course or in my derivation, you have seen that there is an assumption that I consider the line to be lossless. So that's why there is no R or resistance value. Now, if you have any RLC circuit, for example, RLC series circuit, then you know that this damping of oscillation primarily depends upon the value of the R. Okay, so since here there is no resistive part is considered or ignore the resistive part, so it appears to be that it is not there, but actually it is there practical system. So some kind of damping is always there in the system. Okay. Now another thing that underdamped system does not mean that it's unstable. Okay. However, underdamped system means you have higher overshoot, undershoot, okay, higher oscillation. Now you need to reduce the oscillation so that any further, that perturbation should not bring it to an unstable region. Okay, so that is something that can be eventually done by SVC control, or one of the auxiliary, task of SVC is to control that. That is also part of the auxiliary control. Okay, so main control action is to mitigate over voltage and under voltage, and auxiliary control actions are of so many. One of them is to damp the power system oscillation. Now, this oscillation nowadays is very critical thing in any power network around the globe. Okay, and how efficiently you can damp it, that is one of the goal for power system engineers or power system operator. Okay, so SVC can do so. However, don't get misguided that underdamped systems are always what we call unstable. Underdamped systems also can be stable, but it has a very high overshoot, undershoot also, and it takes a very longer time to the steady state. So it is prone to the instability, but it is not an unstable situation. However, if it is an underdamped system, because we have already ignored this resistive part, so possibly that our system is underdamped from the or undamped only. So therefore, this SVG can further regulate the damping, or it can control the damping of the system. Okay, so that's what the answer is. Of course, without even consideration of SVC, some kind of damping is already there in the power system, because some amount of that resistive part is already there. Some amount of power loss is happening. In fact, this power loss or power dissipation, it is basically regulating the damping. Okay, so since power loss is happening to the network, so some amount of damping is already there. But in that case, I ignore the power loss. I assume that it's a lossless system. So therefore, it shows that it is a kind of undamped system. Okay, so actually it is not. The practical power network is having some inherent damping due to the power losses or resistive part of it. But SVC can enhance its damping and it can control. Okay, so that would be my answer. Rahul, is it all right?
Yes, sir. Perfectly understood. Thank you.
So any further questions from those who have joined YouTube live session? You can write your question on the chat box. Any question, whatever is in your mind. Okay. Do not hesitate to ask question, because this is a rare opportunity that I can get some questions from you. And of course, our discussion forum is there, but this is the live. This is the live session, and where you can interact with me directly. Okay. Sometimes in discussion forum, you ask questions and our teaching assistant, they only reply. Okay. So here, even if you are not satisfied with this reply in our discussion forum, you can always ask me in this live session. Okay. So this is a kind of learning, bi-directional learning, you can say. I will also learn from your understanding, and you need to learn from my understanding. Please go ahead and don't hesitate to ask questions. So please go ahead and ask the questions. If I don't see any question next 5 to 10 minutes, then I will assume there is no question. Then we'll terminate the live session. Finish the live session. Please go ahead and ask questions. If I see that there is no question for next 5 to 10 minutes, we'll end up. Any question, whichever is in your mind, you can ask. This is not a kind of normal lecture where I can talk. So if you have any question, then only I will discuss.
Sir, Rahul here.
Yes.
Any exciting new like research topics is there in this field, which for which maybe people are doing PhD or something like that currently?
Yes, yes, of course. So this is a very, uh, uh, what we call widely uh, researched area, and all around the globe, people are working. So one of the areas is, of course, that control of the this type of compensators, which it can be SVC, it can be STATCOM, or it can be any similar type of series compensator. Later on, you will see that I taught you TCSC, thyristor control series capacitor, and so SSSC, and so. Okay. Now, so there are areas direction of research. One is that the control of the compensator for effective mitigation of the over voltage, under voltage, the control of this what we call that uh, damping of the power system oscillation, and power system oscillations may happen due to different reasons. Okay, so appropriate control action is to be required to damp this situation. And also nowadays, you know that our power networks are of very rich uh, in accommodating the renewable energy. For example, that solar photovoltaic energy, wind energy, and so. So this sort of energy, the integration of this renewable energy uh, uh, provide additional challenge to the power system planner and operator. Okay, so this type of power system compensator are even more useful to mitigate those challenges. Okay, now you can heard that a few months ago there is a blackout in Europe, in Iberian countries, and also there was a blackout in Heathrow Airport, London. Okay, you can go ahead and read some of the document, the reason behind it. You will see that this integration of the renewable energy resources makes so many challenges, and uh, their mitigation is not adequate. So that could be one of the reason. Okay, and so therefore these compensators, multifunctional compensator provides many similar type of mitigation aspects. Okay, and all around the world people are doing research. So you can also choose a that PhD work considering this aspect which I discussed.
Okay, sir.
I got a question, but I could not understand that. What is the meaning of that question? It is from Alpha King. Can watch this as a drawer without other cards, sir. I could not understand what do you mean by that. I don't think it is related to this course. Allah, can you just clarify what is your question? So you wrote that my Aadhaar card got cancelled. So can I still get admission to colleges? What admission you are talking about? I could not understand. Anyway, I don't think that you are in right forum. So do you have any question related to the course? Have you enrolled this course or have you registered this course? Alpha? Okay. Any further questions you can ask me quickly. I'll just wait for another 2 to 3 minutes. If there is no question, we will end up this live session.
Sir, we
Yes.
are currently using TSC or basically we are using capacitor to inject the reactive power into the system for various reasons, increase over for the voltage regulation part, sir. So sir, is it possible to I saw somewhere that we can also use synchronous generator to also inject reactive power into the system. So is there any reason why we are preferring capacitive or the TSC to inject the reactive power rather than synchronous generator?
Yes. First of all, that synchronous generators, synchronous generators already generate some amount of reactive power. Okay. Now it generates and it transmits. So however, that we need some local compensation. Okay, synchronous generators are usually located only a few areas in power network, and which are, for example, in India, the synchronous generators are used in thermal power generation or even hydropower generation. They are located far away from the city center where most of the loads are there, most of the customers live. So local compensation is required. That is what the concept of reactive power compensation. Okay. So you cannot connect synchronous generator here and there anywhere. Okay. And they are of huge capacity also. So this type of compensators, they are basically to be used locally. Okay. In a power network where you do not have this sufficient amount of reactive power generation or absorption capacity. Okay, so that is what the difference is.
Okay, sir.
So alpha, your questions are all irrelevant. I don't think you are in right forum. Okay, so if there is no further questions, let me thank all of you, specifically Rahul, for joining to this second live session. I don't think anybody who have joined this YouTube link, they have any further questions. So, or if you have any further question, you will get a last opportunity to meet me on the third live session. Okay. Till then, thank you and goodbye for today. Thank you very much for joining.
Thank you, sir.